Do you want to solve conservation of momentum problems quickly and easily? Maybe not quickly, but easily and the best way? You've come to the right place. This is it. So for a long time, I had my students solve using the standard algebraic method for conservation of momentum problems. But the top students were pretty good at it, but then when you get to two-dimensional problems, they failed. And then the average students, the regular physics students, they had difficulty. And we ended up having to give them the equation, m1v1 plus m2v2 equals it. No, complete waste of time. So we actually kind of avoided conservation of momentum problems for a while because of the mathematical algebraic difficulty. And then the lowest level, the conceptual physics students, we just avoided it altogether. Played with it in pictures and did things like that, but really did not do much with the law of conservation of momentum other than talk about crashes and things like that. There are some good online resources now that we use which are helpful, but back in the day doing this stuff, it was rough. So a while ago, I figured out that, well, why don't we just do this visually? The best method and other methods for solving the law of conservation of momentum problems. Let's learn physics. Visually, as in using the concept of the law of conservation of momentum and the fact that momentum is a vector and there's a before and an after, and you can sketch pretty easily. Let's use that and solve some problems. Spectacular technique, especially for the complicated two-dimensional problems and for the lower level students who just couldn't do any of the algebra or just quit whenever algebra shows up. So here, okay, we know that the concept is the total momentum at the beginning, just before the collision, is the same in magnitude and direction, size and direction, as the total momentum afterwards. So why don't we just set up a grid like this, and up here, I can draw the before picture. So before picture right here, the just before the collision right here, just before the explosion right here. And then just after the explosion, just after the collision right here, after they've lost contact, just before, just after the collision, draw all the objects with their masses and velocities, because momentum is mass times velocity, the product of an object's mass and velocity. And then down here, I can take whatever object I drew up here with its mass and velocity and put an arrow representing its momentum. So mass times velocity, and then mass times velocity, mass times velocity. There's something missing. Like one of these arrows is like, I don't know what it is. So then you just, oh, well, I have everything over here. So I add those up, and this total has to be the same as the total over there. Or I have all the momentum over here, so I add those up, and this total has to be the same as that total. It's actually really cool. So check it out. This is the fabulous method. Actually, what I'm doing here is comparing multiple methods. There's a graphical method, which depends on graphical addition of vectors. There's the standard algebraic method, and there's my method. Mine's, of course, the best. And the graphical method is mine also, but okay, well, let's get to it. Our first problem, a 2 metric ton car traveling east, that's east, at 10 meters per second, collides and combines with a 5 metric ton truck traveling west. There's west. Find the initial velocity of the truck if the combination continues at 2 meters per second west. Here's our equation. The net momentum at the beginning is equal to the total momentum at the end for a closed system. Now these two objects stay the same two objects before and after, and there is no energy entering and leaving the system, no mass entering and leaving the system, no net external forces, and so we can just solve the problem using this. And a common procedure for advanced math is just look at the thing. And so you got 2,000 kilograms multiplied by 10 meters per second, 5 metric ton truck plus 5,000 kilograms times v, and it does seem that it's traveling west. Find the initial velocity of the truck. The combination continues at 2 meters per second west. Combination is 7,000 kilograms. 7,000 kilograms multiplied by 2 meters per second west, which, remember, these velocities have a direction, momentum has a direction, and so you have to put a negative in there. 2,000 times 10 is 20,000 kilogram meters per second, plus 5,000 kilograms times v equals negative, you're going to drop the negative, so watch for that, 14,000 kilogram meters per second. So gather like terms, 5,000 kilograms times V equals negative 14,000 minus, this is negative 34,000, negative 34,000 kilogram meters per second. And the velocity is going to be negative, don't forget that, that's going to be to the left, 34,000, 6 times 5 is 30, so it's 6 4/5, which is 6.8 meters per second, or 6.8 meters per second west, or I prefer the arrow. So that is the algebraic solution. Doesn't look bad, right? But it turns out that that kind of algebraic solution is quite difficult for the average regular physics student. Like they just, they didn't do it, didn't want to do it, horribly unsuccessful. Teachers ended up having to give them, or feeling like they had to give them the equation, like m1 v1 plus m2 v2 is equal to m1 plus m2 in parentheses times v. Especially for the conceptual level, it's just completely, this did not work. So a few years ago, I came up with this new method, which is a whole bunch about arrows and drawrings. Now, the problem solved this way is doable by every student I have. We know that the total momentum at the beginning is equal to the total momentum at the end, just before the collision and just after the collision. So what are we going to do? Well, why don't we just draw the situation before the collision and draw the situation after the collision, and then use arrows to represent the momentum before the collision and the momentum after the collision, and then just make sure that the arrows balance in the picture. Sounds pretty simple, right? Here's a setup, use a grid. So we start out with, and this will be the before, and this will be the after. So draw the before picture. You have a 2 metric ton car, 2,000 kilograms. You can be all artsy and stuff, but not exactly necessary. This is 10 meters per second. And then 5 metric ton, whew, this is a big one. So this is 5,000 kilograms. And this is the velocity that we do not know, so unknown velocity. Then the combination traveled off together 7,000 kilograms, so 5,000 kilograms and 2,000 kilograms. Just put them together and write 7. That's easier that way. Travels together at 2 meters per second west. 2 meters per second west. So the combination, well, this combination 5, 7 times 2 is 14. This combination is the total of 14,000 kilogram meters per second. Now we know that momentum is conserved, not velocity. And so that 14,000 kilogram meters per second is everything afterward. And so that has to be the same direction and magnitude as everything before. So 2,000 times 10 gives you 20,000. 20,000 kilogram meters per second. And then you think about it and you're like, okay, so I have all to the right, all east, 20,000. I have to get 14,000 to the west, to the left. I have to cancel all this stuff and add an additional 14,000. Looks like this is going to be 34,000 kilogram meters per second. And that is the final momentum of this object. Now this arrow represents that, this is represented by that arrow. So P equals mv, 30P equals mv, 34,000 kilogram meters per second is equal to its mass, just its mass, because that arrow represents that object, 5,000 kilogram meters per second times v, oops, you shouldn't go over here, and then that velocity is 34,000 divided by 5, exactly the same answer as before, 6.8 meters per second to the left. There's your answer. Arrow, put an arrow on that thing, it's perfect. This is doable by all the levels of physics that I've ever taught using this method. Using the algebra method, not so much. And then especially when you get to the honors physics and the two-dimensional problems, this method lends itself to spectacular problem solving. It's wonderful. The explosion or recoil problems where you and your grandma on ice push against each other are the first ones generally presented in textbooks, and it turns out that they're the ones that my students have the most difficulty with consistently no matter what I do, because Well, they just don't get the fact that for the initial momentum, the total initial momentum is equal to the total final momentum. They don't get the idea that, oh, well, what's happening beforehand? Nothing. Nothing is happening before. What's happening after? Oh, that's where all the action happens. So the total over here on the right-hand side at the end has to be equal to 0. So the two momenta at the end are going to just cancel each other out because this is a vector equation. You could look at it algebraically this way and say that the 0 momentum at the beginning is equal to the cannonball, 2 kilograms multiplied by 700 meters per second plus 50 kilograms times v. 2 times 7 is 14. 1400 kilogram meters per second is equal to 0 plus 50 kilograms times v. Move everything to the other side. Negative 1400 kilogram meters per second is equal to 50 kilograms times v. And 50 times 2 is 100. This is 1400. That's 28. So the velocity is negative 28 meters per second, or 28 meters per second in the opposite direction, which I didn't draw a picture, so whatever. This is a negative 28 meters per second recoil velocity, opposite the velocity of the cannonball. Now this problem, if you think about it, can be solved with a pretty simple ratio. The 2 and the 700 go together, and the 50. Well, you just 2 times 700, it's 1400. 1400 total divided by 50 gives you the velocity, and you can actually think your way through these things pretty quickly. 1400 divided by 50 gives you 28 meters per second opposite. So simple ratios, you can figure this kind of thing out. What is commonly done is the 1400 kilogram meters per second equals the 50 kilograms times v, and then just solve it. You get 28 meters per second in the opposite direction, recoil. So a couple of different ways to look at it. It's a relatively simple problem, but my students have a lot of difficulty with it without the picture. And here we have that same problem using the exact same concept. The total momentum at the beginning is equal to the total momentum at the end, including direction, because this is a vector, and in the grid. Now, since nothing's happening beforehand, you can make the right-hand side a whole lot bigger. This is 52 kilograms. There's the whole thing together like a big donut. 52 kilograms, and the total momentum at the beginning is 0. So I know that the right-hand side has to be 0 also. This is the 2 kilogram cannonball fired at a high speed of 700 meters per second, 2 kilograms, and this is the 50 kilogram cannon that is recoiling in the opposite direction at obviously a much smaller unknown velocity. So now down here, total momentum. Well, the momentum of this object, 2 kilograms times 700, we know that already to be 1400 kilogram meters per second. Now I know this is the principle that the total momentum on this side has to equal, well, 0. So how do I balance a 1400 kilogram meters per second to the right? Well, I make that a 1400 kilogram meters per second to the left. I could use my little geometry slashes to say that those two are exactly the same size. Now this is momentum, so P equals mv. Momentum 1400 kilogram meters per second is equal to its mass, 50 kilograms times v. And divide that and I get 28 meters per second to the left or west. That's the answer. I think that's a whole lot cleaner, and this again is doable by every one of my students. Force them to draw the picture before and the after, make the little grid, and then look at it and figure it out, the total momentum. Now, here's where this method really shines. For those honors physics students who are solving difficult problems in 2 dimensions, oh, it's beautiful. A 3 kilogram bunch of bananas traveling at 10 meters per second at 20 degrees collides and sticks with a 2 kilogram well-chewed wad of gum traveling 4 meters per second at 130 degrees. Now using our standard 0 degrees and counterclockwise, 20 degrees is this, that first quadrant. 130 degrees is 90 plus 40, which is 50 degrees short of that. Find the final velocity of the combination. So here is the traditional method. You probably should draw this thing. And remember that the momentum is what counts here. So 3 kilograms, 3 times 10 is 30 at 20 degrees. So this is 30 at 20 degrees. Here's a little sketch. 30 kilogram meters per second, and the angle is 20 degrees. And then the other one, 2, 4, 8 kilogram meters per second at 130. So this is 8, much shorter, 130 degrees, which is 50 degrees here, 50 degrees, and 8 kilogram meters per second. And then at the end, you have a momentum which is unknown. So P, I don't know what it is, and the important point is what's my velocity. Now it looks like this thing's going to probably go like this, so I can sketch that for that answer. Now the algebraic method, let me get rid of this thing. The algebraic method would take 30 kilogram meters per second. Here's the x and the y. The 30 kilogram meters per second cosine 20 degrees plus minus, because it's opposite, it's going to be negative, 8 kilogram meters per second cosine 50 degrees. That is the x direction. So I take this component, this x component, that y component, this x component, and that y component. Cosine is associated with the x component. Here's the y component, 30 kilogram meters per second sine 20 degrees minus 8 kilogram meters per second sine 20 degrees, except in this case, oh no, they're both up, so that would be adding. Got to pay attention to the direction here, and then add those things up. So I took those two and added them up and got 30 cosine 20 minus 8 cosine 50 is 23.0, and 30 sine 20 plus 8 sine 50 gives you 16. So I've got 23 positive direction, 16 positive direction. And it looks like the final answer will be in that first quadrant as expected. Now let's draw this final solution. Draw the first vector and then the second one added to it, 16.4 kilogram meters per second. That's the angle we're looking for, and this is the momentum. Gives you the momentum, then you have to divide by the total mass. They stick together, so this would be 2, 3, 5 kilograms. 5 kilograms, and the velocity is unknown. So there's the triangle. Using the distance formula, or the Pythagorean theorem, the square root of the quantity 16.4 squared, leg squared, plus other leg squared equals 28.2, or rounded off to 3. Okay, so 28.3 kilogram meters per second is the momentum. And the angle is the inverse tangent of the opposite over the adjacent. The 16.4 over the 23 gives you 35.5 degrees. Round everything off, whatever, who cares. And then remember that the momentum is equal to mass times velocity. Final step, we're looking for the velocity. Divide by 5 kilograms, which is the mass. You get 5.66 meters per second at 35 degrees. Now, you have this sketch here, which I generally have them sketch with the proper triangle, not having the y component separate from this thing. And then the final answer over here, this is the before sketch, this is the after sketch, this is the total momentum before, that is the total momentum after. Then you set these two up and you add them. And here's a much more visual solution. So draw the before picture, draw the after picture, again, depending upon this concept. The total momentum before is equal to the total momentum after in magnitude and direction. So 10 meters per second, 3 kilograms, that is 30 kilogram meters per second. I have an x component, I have a y component. And 2 times 4 is 8 and 50 degrees. So this is much shorter. This is the x component, this is the y component, and this is 4 times 2 is 8 kilogram meters per second. And this is 20 degrees, and this angle is the 50 degrees, it's right there. All you have to do is have the students take the calculators and then the concept of the components, 30 cosine 20, enter, 30 sine 20, enter. And the other one, 8 cosine 50, enter. 8 sine 50, enter. Put the little one in the little one's place. So this is 5.14 kilogram meters per second. And this is 6.13 kilogram meters per second. Over here we have a 10.3 kilogram meters per second. Big pictures do help a whole lot, so encourage your students, or do it yourself. Encourage everyone to draw large pictures. In 28.2 kilogram meters per second. These are momentum component triangles. So momentum component triangles, once you get the two components, you're going to ignore this. Once you get the two components, you're going to ignore that. Working on the principle that the total momentum on the left-hand side is the exact same magnitude and direction as the total momentum on the right. And this is one object. I just want to combine these two and make one triangle. 28.2 or 25, 23, because these are to the right and to the left, they will partially cancel. This is left, top of the page, right, top of the page. 23.1, rounding everything off. So this would be 23.1 kilogram meters per second. This is still a momentum triangle, but we are ultimately looking for the velocity. And then 10, 16, 16.4. This is 16.4 kilogram meters per second. Hypotenuse. Take some time, and second function, square root of the quantity 16.4 squared plus 23.1 squared, enter. Inverse tangent of opposite over adjacent, 16.4 divided by 23.1 gives you 28.3. kilogram meters per second, and an angle of 35.4 degrees. So here is your angle of 35.4 degrees, and then all I have to do is divide that by the mass to get the velocity. So the velocity is 28.3 divided by 5 equals 5.66 meters per second. This is 5.66 meters per second at, that's the first quadrant, 35.4 degrees. Nice and visual. I really like this. This really improved my honors physics student success. You can also do this using the graphical method. Now, that's a pretty spectacular one that nobody ever does. So we've got the 3 kilogram bunch of bananas at 10 meters per second. And the 2 kilogram well-chewed wad of gum, 130 degrees, 4 meters per second. Here's a quick sketch, the before, the after. Got to do that. And then there's the before total and the after total. So that plus that equals that. And you're like, oh, well, I can just add these things like regular vectors, right? Pick a starting point that's like right there, there. Try not to use the same marker that should probably not be used. Use a skinnier marker. Measure this angle, line up that protractor really carefully, and then measure 20 degrees, mark 20 degrees, and using some kind of scale, 30, 3 times 10 is 30, 4 times 2 is 8, 30, make that, I don't know, 6 centimeters long. Longer it is, the better. So this is pretty much the minimum that you would want for this procedure. 6 kilogram meters per second. Sorry, that's not correct. 6 centimeters and 30 kilogram meters per second. And then that plus this 8 kilogram meters per second. So that's 6 centimeters, 30. 8 is 1.6 centimeters. Diagram's way too small. Anyway, let's see what we get. So line this baby up as carefully as you can. At the tip of it, 130 degrees, 90, 100, 110, 120, 130, right here. Measure that at 1.6 centimeters. .6 centimeters. In that direction, this is 8 kilogram meters per second, 1.6 centimeters to remind you of the scale. And then connect the beginning point and the ending point. Here's the end, beginning So the momentum arrow, momentum direction will be 36 degrees. It's at 36 degrees. And the magnitude, 57. About 58 centimeters, 55.8, 29 kilogram meters per second at 36 degrees. And that represents the combination. So 29 divided by 5 is 5.8, which is 5.8 meters per second at 36 degrees. It's pretty close, and it's a whole lot faster. Good numbers. Here's a fun one. 2 kilogram grenade falling at 20 meters per second. Suddenly, it explodes into 2 pieces, moving before, 2 separate pieces moving afterward. Algebraically, this one is a difficult problem. It's a solve and substitute thing. Not too easy. Anyway, you start out with a 2 kilogram grenade falling at 20 meters per second. So here is your 2 kilograms and 20 meters per second. You then have these 2 other pieces, a half kilogram piece. This is 2 kilograms at 20. So a half kilogram piece over here, 1/2 kilogram moving 15 degrees to the right of down. So this is 30 meters per second. And this angle is 15 degrees. And then over here, find the final velocity of the other piece. Okay, so it's 1.5 kilograms. And you take that thing and it's got to go probably in this direction. I don't know, but I don't know what the velocity of that thing is. So I have to find components of this. And remember, momentum components. This is 40 kilogram meters per second. I know that the initial momentum and total momentum over here is going to be the total momentum over there. And I have to split it into x and y components and then try to substitute and solve for an angle and for a velocity. So velocity, magnitude, and direction. So let's take a look at that, x direction. So in the x direction, the total momentum, again, equation is equal to, this is the x. Momentum, 2 times 20. Down, we're using the down is positive, 2 times 20 is 40. 40 kilogram meters per second is equal to, and we'll use this as the angle theta. So use my velocity over here, don't know what the angle theta is, and so that would be 1.5 kilograms times v times the cosine of theta, which will give me the, in this case, the y component, and then plus half a kilogram, 0.5 kilograms times 30 meters per second times the cosine of 15 degrees. You see the problem here? Unknown and unknown. We can cancel these things out, make it a tangent or something, but this does not look like fun. Sorry, this was the y direction. Then in the x direction, this is 0 equals 1.5 kilograms times v times the sine of theta plus half a kilogram times 30 meters per second times the sine of 15 degrees. So I switch my x and my y, but it doesn't really matter, whatever. But this and that, it's got to be visual. They have to put them together in the right place. Then 1.5, this is going to be, I can drop all the units to make it simpler visually. 1.5 v sine theta. So be 15 sine 15 equals 3.88. Plus 3.88 kilogram meters per second. But wait a minute, these are going to be opposite. That's that way, that's that way. Maybe I should put a negative in here. Or make that positive, make that negative. And that's one of the problems with this method, depending on algebra. You have to have the negatives correct or you're going to have serious problems. Now, this will probably take care of itself, but ugh. So this is 40 equals 1.5 v cosine theta plus half of 30 is 15. 15 cosine 15 plus 14.4. Everything's positive, that's down. I assume that's down, that's down. Then I have to do a substitution. I have to solve this for v, substitute into that one, get an answer. They give up. Students absolutely just straight up give up. Unless you're really, really, really good at math and highly dedicated, you just totally give up on this one. So I'm going to also. And then I'm going to show you how to solve this thing graphically. Well, not really graphically, but the component method, which is totally visual, which is so much better. Anyway, complicated algebra problem. Now this is the graphical method. So you pull out your bag of tools. You won't need that one. You probably won't need that one or that one, but man, they're really nice to have. The two things you need are this. This is graphical addition of vectors. It works the same for static equilibrium as it does for navigation, as it does for moving explosions and momentum. And so we know that this is going to be that plus that. Well, if I draw one, that's the solution. Then I draw the second one, and then fill in the third one. This is actually really, really, really simple. So 40 kilogram meters per second. I'm going to start that thing right there. Oh, look at that. There's just about enough space for 8 centimeters. Very carefully draw the length of this to be exactly 8 centimeters long without letting the bleed make it longer. So that is 8 centimeters and 40 kilogram meters per second. So 40 kilogram meters per second and 8 centimeters just as a note for the scale. Now this is 15 degrees from the vertical to the right. So lining that thing up at the very beginning where it started, set this thing up 15 degrees to the right. Probably not the best pen to use, but 5, 10, 15 degrees to the right of down. Use that one. And this is 15 kilogram meters per second. So that will be 3 centimeters using the scale that I have over here. Line up, draw 3 centimeters. There is 15 kilogram meters per second. And then the answer, again, this marker wasn't the best choice, but whatever, who cares? This start here and there. It's in this direction. That plus that equals the sum. So again, sum, that plus that, that plus that. Then measure the resultant, measure the leg of this little triangle, not a right triangle. This is about 5.2 centimeters long, 5.2 centimeters. This was 3 centimeters, so this would be 26 kilogram meters per second. And the direction, here's where it comes in handy. Direction of this thing, lining up the protractor properly and then double checking and triple checking it. This is about, what is that, about 8 degrees left, maybe 9 degrees left. At 9 degrees left of down. Now that's kilogram meters per second. Divide that by the mass of the thing we don't know. 26 divided by 1.5 equals 17.3. 17.3 meters per second at 9 degrees left of down. There we go. Really close answer to the official solution using algebra. And once you get this taken care of, then it's relatively easy if you know how to add vectors and then just divide by the mass. Really, really, really good situation. Use a lot of paper for this one. Probably rotate it, but I'm using a sideways screen. So rotate it, use a lot of paper, and you can get really good answers. My regular students can get excellent answers this way. All right, here is the situation. Make the grid, and then where's the 2 pieces? There's 2 pieces on the right, so leave a whole lot more space for that one. 2 kilogram grenade. This is 2 kilograms falling down at 20 meters per second. Explodes into 2 pieces. A half kilogram piece, so here is a 0.5 kilograms. Try to make it smaller, but it's difficult to write and make it smaller. Half a kilogram piece, 30 meters per second, 15 degrees to the right of down. So here is the 30 meters per second. And here is the 15 degree angle. Then over here, this 1.5 kilogram piece, 1.5 5 kilograms, much larger. Travels off in this direction somewhere, don't know what that velocity is. So let's make this thing visual. This is 2 times 20 is 40. 40 straight down, 40 kilogram meters per second. And then this one over here, this is what I know, so you work with what you know. Half times 30 is 15. So what I'm going to do is make a component triangle for the momentum. This is half of 30 is 15 kilogram meters per second. There is the y component and the x component. This is an angle of 15 degrees. So 15 cosine 15 and 15, I did these calculations already last time. 15 cosine 15 and 15 sine 15 gives you those two components of momentum. And those are 14.5 kilogram meters per second. And this over here is 3.88 kilogram meters per second. So this right here, this momentum plus this momentum has to give you that momentum. So the first thing we can do is draw the x component. I know that since there is no x component over here on the left-hand side, there has to be no x component on the right-hand side. So I know that this is 3.88 kilogram meters per second. And then 14.5, well, it has to be 40. It's only 14.5, so that would be 25 and a half. 3.88, this is nice and big. If you have space, use more space. 25.5 kilogram meters per second. Then find the hypotenuse. There's the angle. Second function, square root of the quantity, 25.5 squared plus 3.88 squared gives you the hypotenuse of 25.8 kilogram meters per second for that momentum. And then inverse tangent of 25.5 divided by 3.88 equals 81.3 degrees. Put those little numbers in here. This angle is 81.3 degrees, and this is 25.8 kilogram meters per second. Mass is 1.5 kilograms, and so just like I did before, mass times velocity, I'm going to take momentum, divide by the mass to get the answer. 25.8 divided by 1.5 is equal to 17.2. It's 17.2 meters per second. Same direction. So 25.8 divided by 1.5 gives you 17.2 meters per second at 81.3 degrees. This is 0, 90, 180, 81.3. We're using the same standard as before. This angle over here, 90 minus 81.3 is 8.7 degrees at 8.7 degrees left of down. Now that right there, that is a solvable problem. That I can do. That all of my honors physics students can do if they focus. The other one, the algebra, half of them give up immediately. This method is spectacular. It's very visual, and it's excellent. I've had excellent success with the lowest level and the highest level solving really difficult problems. This one can also be solved graphically. It's pretty cool. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.